So thanks everyone for coming. I realize for the Americans in the room, it's the day before Thanksgiving. I'm a research scientist at the Applied Physics Lab of the University of Washington. And I'm going to talk today about a software toolkit that I've been developing called Icepack. And I've been doing this with some students as well. So I pointed out Andrew Hoffman and Jess Badgley. So I'll show some of their work towards the end. The very brief pitch is it's pretty good. You should try it. I think it's all right. And I have funding to develop it from NSF and from NASA. So I think the project has at least a couple years of legs on it. And also my career sort of depends on people using it. So I'm very, very motivated to be as helpful as I can if you do try and actually use it. So I'll put some links to the website in the chat at the end after I've taken questions. And I'll have my email address and the repository page for it and everything. When Ellen Enderlin gave her talk, she talked a lot about how she got where she was in her career. And I thought that was really nice, and we should be doing more of that in these sorts of things. And I think if I kind of roughly go over how I got to even thinking this is a good idea to embark on this path at all, I think it'll help illustrate why I'm doing it. So I started doing my PhD in applied math at the University of Washington in 2010, not really knowing what exactly I wanted to do. And we have a requirement to work with people in other departments because it's applied math and not just navel-gazing math. So I did one project with a professor in atmospheric science, and I just biffed it completely. And he probably thought I was an idiot. And you know, I was 22, I probably was an idiot. So I was sort of despairing a bit, and at one point I met Ed Waddington, and he suggested that I go to the weekly glaciology lunch because he thought maybe I'd like working in glaciology. And I went, and you know, I'm not the most social person in the entire world. I showed up and I was all nervous because I didn't know anyone. And I had a conversation that went roughly like this. So we were doing introductions, and everyone was going around the room and saying what they worked on, and people did all sorts of stuff I had no comprehension of. And it got to me, and I said, I'm Daniel. I'm doing an applied math PhD. I think glaciers are pretty cool. But mostly what I know about are finite. And a gentleman from the other end of the room just cuts me off in mid-sentence, and he says, "You do finite element methods. Do you need an advisor?" And that was how I met Ian Jochen, and I have been a proud thorn in his side ever since. So he was one of my advisors, and Randy Levesque was one of my other advisors. And I stayed on for a postdoc, and now I found some money, so they're going to let me stay on at APL as a research scientist, provided I keep bringing home some money. Some things that I did during my PhD, I got really into coding pretty quick. So the first project that I'd worked on that I just got no results on, at the time I thought that it would have helped if I had known a lot more Fortran. So the first thing I did was I decided I was going to use this as a chance to learn a whole lot more Fortran, and I wrote a finite element glacier flow model all from scratch in Fortran. Which was very educational and totally useless to anyone other than me. And I used Elmer Ice for a while, which was a lot of fun. At some point, I had this kind of come to Jesus moment because I realized I wasn't sure what the job prospects were for me. And I figured if I wanted to make it in the private sector, possibly, I was going to need to learn C++. So I took this as another opportunity to learn another programming language. And I used a software library called DEAL2 for finite element analysis. And I wrote another ice flow model using DEAL2, and this involved doing things like rolling my own code to calculate variational derivatives and things like that, which was laborious, and I got tired of that, and here we are. And I'll explain where exactly that is in a moment. So when I got into this, I had a lot of assumptions about what I was doing and why I was doing it, and a lot of them were wrong. And so from the get-go, Ian recruited me in the first place because people in glaciology needed modeling expertise, and they were willing to go, train an applied mathematician at great cost out of his grants to do it. And the reason that I believed they needed it was because I thought that people had a problem, and that was that doing really big computations really fast is sort of a rate limiting factor for them. It's the thing that's the barrier between them and getting research done. And the reason I believed this was because that was what my PhD was preparing me for. That was all the courses I'd taken were about, cache coherency and parallelism and all these things you need to know to make things run on supercomputers. And this assumption was wrong. And I will explain this to you as follows. So, so while I was doing my degree, I met a lot of students in earth sciences who had a very different background from me. And to zeroth order, pretty much all of them needed to do some modeling at some point. But one thing that I observed was that a lot of students would hit roadblocks, they would get frustrated with the whole experience of trying to do modeling, and very often they would give up. And just as a hypothetical, have you ever seen a student go through this with field work? I mean, I know it happens, but I think it's pretty rare that you could take someone to a place like this and have them say, no, I don't ever need to do that again. You know, I'm staying home. But I have seen students go through the experience of trying to use numerical models and think like, nah, I didn't like that much. So I have no data to back up this assertion, but I'll hypothesize that the attrition rate out of numerical modeling is higher than the attrition rate out of doing field work. And as an aside, I'll take this opportunity to thank Seth Campbell and the Juneau Icefield Research Project for taking this nerd outdoors. The one on the left is one I took of the Gilkey Trench, and the one on the right is looking upstream of Taku Glacier. And that was at about 11 at night. So the conclusion that I drew from all of this was that the real rate limiting factor for a lot of people is developing a level of proficiency with computational things and with numerical modeling in the first place. And by the time people have developed that proficiency, the whole issue of, well, I need my code to run faster, usually you've developed a level of comfort with the tools in the first place that you're empowered enough to feel like you can make those kinds of changes and learn about those sorts of things, you know, what you need to know to make things go to supercomputers if need be. But the other thing is, not everyone needs to run really big computations. Most of the simulations that I run, I do on my desktop or on a laptop. Now, I realize that a lot of this is field dependent. If I were doing, say, ocean modeling, then that would be very different. For a lot of, you know, or for climate modeling, it's really kind of go big or go home. But I think in glaciology, there's a lot of really interesting science you can do with very limited hardware. And in that case, the thing that I really wanted to address more was, how can we lower the barrier to entry? How can we make it easier for people who don't have a whole lot of background to get into doing numerical modeling and doing it well, and making useful results out of it? So this is really the question that I've tried to work on most, and the things that I'm kind of the direction that I'm going towards with Icepack. So as an aside, and I'm going to repeat this many times, all simulations begin life broken, unless you're exceedingly lucky or like really, like I'm not that smart. I've never written any bit of code that works the first time around. So this is really a big thing I was considering in how I designed a lot of this. Also, I have this wonderful logo that was designed by one of the students from JERP. That would be Jeremy Stock. So if any of you ever need a logo design, let me know and I can put you in touch. So how did we do this? So I built Icepack on top of another package called FireDrake, which is for finite element analysis. So probably up until around 2000, 2005, kind of the standard way to develop these things was that a library for finite element analysis would provide you with data structures and algorithms for things like describing an unstructured or irregularly shaped domain, and it would provide you routines for calculating basis functions and gradients of them and things like that. The last 10 to 15 years have seen a new innovation that is sort of a marriage of symbolic computing, if you're familiar with Maple or Mathematica or SymPy or Wolfram, with numerical computing, which is just, you know, solving big nonlinear systems of equations. So what FireDrake does, and what many other similar packages do, is they have something called a domain-specific language, which is used to describe the problem that you're solving. In our case, they'll be weak forms of partial differential equations. And from this symbolic description, they will generate optimized C code on the fly in order to assemble that system of nonlinear equations. So a lot of the stuff that I'd been doing before that I had written all pretty much by myself in Fortran or with a little more help in C++, all of that gets generated for you, which is really amazing because it's not very fun to write it. And I can tell you because I've done it a lot. And also another important thing to note is their logo is this silly little dragon with his horns all akimbo. So you can tell that the people who develop it have a good sense of humor about themselves, which is very valuable if you constantly pester them for assistance. So just to give an example, so I'm not going to throw a ton of math at you, and this is pretty much all, and you don't even really need to understand this. The important part is that what this new innovation of using domain-specific languages helps is that the code you write is almost identical to the math. So what I've written here is the weak form of the Poisson equation for a field U is the unknown, and the code that discretizes it looks very, very similar. So here the dot product between the gradient of U and the gradient of V is replaced by a call to a function called inner for the inner product. And rather than some upside down triangles, we have grad for gradient, and dx is dx, and so on and so forth. So this makes it really nice. There isn't a whole lot of extra kind of noise and all these loops you have to write in C or Fortran surrounding the actual math. It kind of lets you get really quickly to the good part. So this is really kind of a new, and I think this is really an amazing innovation, because a lot of the research in computational science for the past several decades has been singularly focused on how can we make code that runs faster. This is something that helps you, the physical scientist, run faster, which I think is really cool. It makes you more productive. And if you're looking at a cost-benefit analysis, my salary could buy a lot of computers. So my time is much more expensive than computer time. And that goes even more for all of you. So what these tools have automated is the process of setting up physics problems, but I also don't want to give you the impression that they're magic or that they do absolutely everything for you. They automate away by far the most error-prone step of the process. And having done that by hand, I can tell you it's very error-prone. But a lot of the responsibility still falls on you. You have to decide on solution methods. So for example, what I wrote down before was an elliptic differential equation, and there are certain solution strategies you would use to actually calculate the unknown field. And those would be different if it were, say, a hyperbolic equation instead. So this is what I mean when I say you still have to make sure you're solving the equations right. And for ice flow, that means doing things like computing an exact solution to, say, the shallow shelf approximation and checking your numerical solution against it to be sure that you did everything correctly. And the second and arguably more difficult and interesting challenge is making sure that you're solving the right equations. So comparing the results that you get from your simulations to real observational data and making sure that they actually describe the world. Firedrake kind of sits within a whole other ecosystem of other packages. Another tool you probably might have heard of if you've done any of this is called Phoenix. So Firedrake was an outgrowth of Phoenix. It sort of forked off 5 or 6 years ago, but the two communities are very friendly. So Phoenix has a very heavy remit for doing computations in biology. So a lot of what they like doing are things like simulating blood flow in the heart. And that comes with its own special challenges. The people who develop Firedrake are very heavily invested in geophysical applications, and that has guided the sorts of features that they've added to it. And there are a lot of other tools that people have developed on top of it. So there's an ocean model called Thetis, and there's also an atmospheric dynamical core called Gusto. And the figure that I've shown below is from Gusto. This is the Williamson 5 test case for shallow water, the rotating shallow water equations on a sphere, and that's from Colin Cotter. And I show it because it looks cool. So there's talk of at some point we're going to couple all these together and we'll make a whole complete Earth system model many years down the line, probably. So I told you roughly what Firedrake will do for you. So then there were many things that I had to do on top of it. So first was defining the various diagnostic models of ice physics. And one of the things that I had to do is, so Firedrake makes it very easy to specify what physics problem you're solving and to then choose what kind of solution methods, but all the other software architecture on top of that is on you. So one of the things that I'm especially proud of, and that I'll show in a second, a demonstration, is that all the models that I've added are flexible and you can modify components of them. So if you want to change the sliding law, that's easy. And if you want to add new fields to some of the parts of the physics, you can do that. So right now, for example, the sliding law takes in as arguments the ice velocity and a friction coefficient. But if you wanted to go crazy and add hydrology to this too, you can even change the number of arguments by also adding, say, the effective pressure as an additional diagnostic field. So one of the things that they let you do is choose what kind of solution method you want to use. It was also on me to decide what some good defaults were and to actually test them and make sure they were fairly robust. So the equations of motion of a glacier are quite nonlinear. So there are certain decisions that you have to make about numerical solvers, and I had to implement a lot of these myself. The third thing I had to do was implement data assimilation procedures. So if you give me some observational data about a glacier and you want to back out some field that cannot be observed, and I'll show some examples of this later. So for example, taking some remote sensing measurements of the velocity of a glacier and estimating what the friction or the viscosity was. I had to do a lot of that. But FireDrake will help you by calculating a lot of the variational derivatives for you. So there's a lot of the error-prone stuff becomes their problem and not yours. And finally, and the one that I think never gets quite enough attention, is documenting the daylights out of everything. So as I've kind of alluded to before, I mean, half of my mission is developing a new tool, and a lot of it is technical stuff like making sure this nonlinear solver converges and things like that. And the other half is educational, which is creating the kind of tutorial materials that will make it easy for students to pick it up and use it really quickly, and that won't require a whole lot of knowledge that they are unlikely to have given the kind of background that you get. And I'll show you some of that in a second. So just as a brief summary, the physics that we have implemented so far. So we have some 2D depth average models. So Jess Badgley implemented the shallow ice model. The first one I wrote was the shallow stream equations. The past 2 years, we added a 3D model, which is the first order or Bladder-Patten equations. I had to use, to implement it, I had to deploy chutzpah in the extreme. So if you're curious, ask me about it. It was great fun. There was a lot of stress eating, but I got it done. And other processes like heat transport and damage mechanics. So the new things that we had, I add new kind of components to this based on what NSF or NASA have paid me to do. But also that's partly guided by the community as well. So if a lot of people are asking me for, we want Fern, then it's going to be my job to add Fern, or find a willing student who's interested and stoked enough to try and add it themselves. And we have found a few students who have added some of these things as well. So after this talk is over, the number one item on my to-do list is something for dynamic geometries and calving. And after that, full Stokes. Some of the students I work with are interested in fabric evolution. So we're talking about how we're going to do that. But again, taking requests. So if there's something that you'd really like to see added, then please let me know. So time for a demonstration. So I have a way to run all of this through the browser, and if any of you are curious and want to try this, then let me know. So what I'm going to run through is the second demo from the Icepack tutorials. So I'm just going to briefly show you. So this is the repository page for Icepack, and we have a bunch of Jupyter notebooks that are in here. And this is the one on synthetic ice shelves. So we have a whole bunch of these, and I'm sure many of you have seen Jupyter notebooks before, but if you have not, it's a format that allows you to interleave text and code in Python or in other languages along with mathematics, and it'll put all your plots in there for you. And I think they're really invaluable as an educational tool. So you can run all these cells of code independent of each other, and they'll generate all the plots on the fly. So I'm not going to run through all of the details of this. I mostly just want to show you, like, this is roughly what the tutorials look like and some of the things that you can do with them. So for this one, what I was doing was setting up a simple example of an ice shelf where the geometry consists of the intersection of two circles, which is roughly of a size meant to mimic the shape of, I don't know, something like Larsen C, but with most of the complexity taken out. So the first thing that I had to do was generate a triangular mesh of this domain. So this one is a little silly looking. Just for an example, I wanted to show you, this is one that I also have for the Larsen ice shelf, which has a plot of it. And I've always put in these little legends because the different parts of the domain boundary are shown in different colors. If you've done any numerical modeling, I would say there is a 100% chance that you've screwed up adding the boundary conditions at some point. And I've wasted God only knows how many CPU cycles because I interchanged a 1 and a 2. So I added this stuff that'll show it to me in nice colors, so we'll never make that silly mistake again. Anyway, so this is one for Larson, but for this synthetic example, we're just going to look at something much simpler. So I'm going to go ahead and run this. Of course, when I tested all of this in the first place, it runs lightning quick, and then I didn't realize that when I'm also in a Zoom meeting at the same time, the simulation slows down just to be just a little slower than I'd like. So I'm going to go ahead and run the last part of this, and while that goes, I think it takes about 6 or 7 minutes. So I'll go back and talk about the rest of it, and hopefully by the time I'm done yammering, it will have completed. So I've created the geometry of the domain using this external tool called PyGmesh. Then what I'm going to do is create some totally weird input data, which we're going to spin up to something near steady state. So this is sort of a spin up experiment. So what I've done is created this really gnarly mathematical expression through a whole lot of trial and error that definitely did not emerge fully formed for the thickness. So what I wanted to have was something where there are these bumps of thickness at the inflow boundary that represent some ice streams that are flowing into this domain. But obviously I can't just figure out off the top of my head what the steady state of this ice shelf was. So what we're going to do next is run this forward by a few hundred years until it's roughly in steady state. One of the things that I've tried to do throughout designing this tool is try and have a clear separation between things that are responsible for what and things that are responsible for how. So in this cell, I've created a model object, which is this class ice shelf. So what this says is that we're trying to simulate an ice shelf and that there are various terms in the diagnostic equations, one for viscosity and one for gravity, and that's basically it. If we were looking at ice streams, there would be additional terms for friction. And if we were looking at a 3D model, there would be terms for kind of the 2D membrane component, and then there would be another term for the 3D vertical shear component. But the ice shelf model is quite simple. So this is the what part of the equation. The next part is to create a solver, and this is an object that's responsible for actually numerically solving that large and nonlinear system of differential equations. And the important part about separating these things is that different people are going to be interested in touching different parts of the code. So if you're a glaciologist, you might be implementing new models, you might be modifying parts of an existing model, you'd probably be experimenting with the physics. You may or may not care about what the various strategies you use are for actually solving that system of equations. But if, for example, if I had a PhD student who is in applied math, they would probably be more interested in how we're solving them and, say, in implementing better optimization solvers. And this is something that would go into this flow solver object. The other thing that's interesting is that there are many different models, but we can use the same, essentially the same code to solve every one of them because there are so many commonalities between them. So there's one flow solver, but there are many flow models. So next, I had to define some other inputs. So we're saying the ice temperature is 255 degrees Kelvin, create some initial data. And here is kind of the first taste of actually solving anything. So the solver object has a method called Diagnostic Solve, where you put in the initial guess for the velocity, the thickness, and the ice viscosity. And here I've plotted the initial value of the thickness. So thinner is earlier in time and thicker is later. So you can see the flow direction is roughly from bottom to top. And finally, this is kind of the good part. So here what I'm doing is repeatedly calling two methods of this solver object in lockstep with each other. So you can think of pretty much the simplest ice flow models as composed of two parts. There's a prognostic equation, which describes how the thickness changes in time. And second, there's a diagnostic equation that describes the velocity as a function of the thickness instantaneously. So I pretty much designed the entire package so that I could write this loop, which is that for every time step, you first update the thickness. That's called a prognostic solve, which takes in the time step, the current thickness, the velocity, accumulation rate, and the inflow thickness, and then update the ice velocity, which is called a diagnostic solve, which takes in the velocity, thickness, and the viscosity. So here, I'm also injecting a bit of extra code. So what I'm doing is I created a list called H's, and I'm appending to that list a copy of the thickness at every time step. And the reason I'm doing that is so that I can save all the thicknesses and make a movie of them later. So the other thing that I think is really nice about this is that, so it's a simple loop to create this entire simulation. Oh, there's one other extra little detail. I've used this package called TQDM, And that lets you have this nice little progress bar below. And actually, it's still running, so we can see it going here. Yeah, so this gives you an idea of how long a simulation is going to take, which having this kind of feedback is really nice. You know whether you should just, maybe make another cup of coffee or go and make dinner. So having feedback and progressive evaluation is one of the things that I've tried to design for a great deal. So again, the loop is basically just a simple alternation between a prognostic and diagnostic solve, but you can also put whatever arbitrary other code you want in here. So for example, if I wanted to generate plots as it was going, if I wanted to print out the minimum and maximum thickness values or minimum and maximum velocity values, whatever crazy thing your heart desires, your imagination is the only limit. And again, this is going back to what I said earlier, all simulations begin life broken. So I definitely screwed this up the first time I wrote it, but I can't recall exactly how. But being able to put in kind of arbitrary diagnostic code to insert your own sanity checks is really valuable for debugging. And you'll write code once, but you'll debug it many, many more times. Because again, all simulations begin life broken. On top of that, so here I've written it as a loop. It's understood that I'm going to be going through and taking 200 time steps. But if you wanted, you wouldn't even necessarily have to run it in a loop. If things were really, really broke, you could just manually tell it, okay, give me the next thickness, give me the next velocity, then put in whatever analysis code you want so that you can figure out what in God's name went wrong. Then iterate it by one time step manually, and you can do the absolute lowest level thing possible. So I've tried to engineer it so that you have very fine-grained control over what exactly happens within a simulation. Again, with a view to the fact that I make mistakes all the time and I need a way to recover from them. Let's drag this back to the beginning. So here you can see the very silly initial thickness. And as the simulation progresses, those ice streams, first they flow into the main body of the ice shelf, and then they start to push each other apart and bend. So you can see these two have diverted each other from their course, which I think is very interesting. So all of this is pretty bog standard, very simple simulation of an ice shelf. Again, it may be easier to use or easier to insert whatever debugging code it is you want. The next part I want to show you is, I think, something that I'm very proud of, which is the ability to change the physics and to play around with them in some non-trivial way. So this is from the tutorial. One of the things I wanted to do at the end was show people different ways to analyze the solutions that you get out of this simulation. So, I mean, obviously plotting things is nice and making pretty pictures is important. Here what I was showing was how do you calculate the flux of ice into and out of the ice shelf. And I think this is nice because it illustrates some of what I was talking about the domain-specific language. So here the flux of ice out of the terminus is the product of the thickness and the inner product of the ice velocity u with the unit outward normal vector nu. And we're integrating this over the edge of the domain. So I've specified that we're using a measure ds instead of dx. And we're integrating over only segment 2. So if I go over to the Larsen ice shelf, for example, the terminus is segment 1 in that example. It's segments 1 and 3. So that's what those numbers correspond to. And likewise, the inflow boundary is segment 1. So here you can calculate, for example, that the flux out of the domain is 38 cubic kilometers a year, and the flux in is 38.14. So it's roughly in steady state by the time this simulation is finished. And the other thing I want to draw your attention to is the fact that, this h times inner of u and nu looks very similar to the math you would write of, h times u dot nu, for example. So again, I didn't have to write a loop or anything to iterate over every edge of the boundary of the mesh. Instead, I create this symbolic description. And when I pass that to this function called Assemble, then it actually gives me a floating point number at the end. So, again, just a small taste of what I mean by this domain-specific language that they've created, and it's embedded completely in the syntax of the Python programming language. That was kind of the first part of the tutorial. The next part, this is some work that Andrew Hoffman, who's a student at UW-ESS, did. So he was interested in continuum damage mechanics, which is some way of incorporating the effect of crevasses and rifts and how those affect the overall flow field. So Torsten Albrecht and Anders Leverman had a few papers from some years back on this. So the idea is that you can introduce a new field into the simulation, which is called the damage, and which we've written as D. And this acts as a bulk increase in the fluidity of the ice shelf. So this field D takes values between 0 and 1. And since 1 minus D goes to the power minus n, this increases the overall fluidity. And you then write down another differential equation for how the damage field evolves in time. So in order to incorporate this, what we did is we took the existing function within Icepack that calculates the viscosity of a glacier, and we redefined it so that it would also take in this additional field, which is the ice damage. The reason we're able to do that is that all of these arguments are always passed by keywords rather than by position. So you can pack more fields into a dictionary, and if the right function that calculates that part of the dynamics doesn't care about a new field, then it just ignores it. So again, this is only a few lines of code. And so before I talked about creating a model object and creating a solver object. So here I've created a new way to calculate the viscosity, and I'm passing this to the model object to create this ice shelf model where we've altered one component of the dynamics. And again, the solver doesn't really care about what model it is you're interested in. So the solver works essentially the same way. So here this is, if you're not familiar with Jupyter Notebooks, again, this is a nice illustration. We can combine all the code and explanatory text, and also the mathematics are typeset nicely in LaTeX, so we can show equations too. So some of the inputs to this damage model that Andrew implemented are the the strain rate and the membrane stress tensor. So here what I've done in this cell is calculate the strain rate tensor, which you can recognize as the symmetrized gradient of the ice velocity. I'm sorry, my cat is interrupting. And so here I've plotted the absolute value of the strain rate. So one of the interesting things I find in this is that, so these kind of curvy bits are where the ice streams are, but the areas where the strain rate is highest are in between, which I think is sort of interesting. And which makes sense if you think about it for 2 seconds. But so we should expect to see the most damage not in the ice streams themselves, but in the spaces between them. So then the next part, so similarly, before I had an ice flow model object and a solver object for it. So here I'm creating a damage model and a damage solver. And likewise, you can customize the damage solver by, say, changing the rate coefficients that specify how fast damage evolves in time, and other kind of physical parameters like that. And now we have a slightly more interesting loop. So this is very, very similar to what I showed you before. So first, we update the ice thickness by 1 time step. Then we update the ice velocity. And here, before, the only arguments we were passing in were the initial guess for the velocity, the thickness, the viscosity. Now we're also passing in the ice damage as an extra parameter, and everything works fine. You can just add more fields as you like. Finally, we actually get around to updating the damage, which involves first calculating the strain rate and the membrane stress tensor, and calling the damage solver, which takes in as arguments the damage, velocity, strain rate, and so on and so forth. So this, I'm really pleased with this kind of ability to add in new components of the ice physics and to modify existing ones. So the same sort of methodology would apply if you wanted to. If you were crazy enough to implement a hydrology model, then you could also implement that and have it coupled into the ice, the friction coefficient for a grounded glacier. And given that we don't understand everything about ice flow, I think I really like the fact that we can take this and modify components of the ice physics and tweak them to your heart's content. And here's the final value of the damage field at steady state. So one of the interesting things is, so the strain rate is highest in between the ice streams, but continuum damage mechanics has this thresholding behavior where you only get sources of damage if the membrane stress exceeds some critical value. So there's only 2 of the ice streams where the membrane stress was sufficiently high to actually give you an appreciable value of the damage. And that was pretty much all I wanted to show you about that one. So this, again, just to reiterate, this runs in, 7 or 8 minutes on my little laptop, even when I have Zoom running. even faster when I don't. So being able to get that kind of real-time feedback is very nice, especially when you're first getting started, and you know, you don't have to wait a day to find out the thing's broken. So that was most of the demo I wanted to show. And again, if you want a way to run this yourself, then get in touch. I have a way that you can just run it through your browser without having to install anything. So let me know. So I've done this before when I've run workshops for Icepack, where we went through this whole business of setting up some server running in the cloud where everyone could get it. But there are too many people here, and I don't have enough money to let you all run all the code on my dime, no offense. So we're gonna have to make do with this. So just some of the takeaway messages I wanted you all to get from this, which is that you as a user of this, you control what the simulation does, and you control it at a fairly fine-grained level. You can step through it manually, you can add your own diagnostics, you can add your own sanity checks, but you should largely not have to concern yourself with how. That's my job. So I submit that I've written some pretty robust solvers for the very nonlinear equations of ice flow. But it's something we're always working on and trying to find new ways to make it easier. One of the problems we run into is if people put in some kind of ridiculous value for some field, a thickness that goes to 100 kilometers or something absurd, then sometimes it can break. It can even work for some moderately ridiculous values of the inputs, but we want to have it so that it can give you an answer even under absurd circumstances. And then it should be on you to recognize, like, oh, something about this result makes no sense. So that's something that we're always trying to improve. And most importantly, it's pretty easy to modify elements of the model physics, change the parameterizations, add new physical processes, go crazy, man. So I've also done a lot of work on Dado Simulation. This is pretty much what keeps the lights on for me. So this is backing out unobservable quantities like the ice viscosity from remote sensing measurements. So this is something I've done for Larsen C, where we've taken the measures, ice velocities, and the bed machine thickness map of the Larsen C ice shelf. So the left shows in the end, the computed value of the ice velocity, and on the right, we were backing out the fluidity of the ice shelf. I should specify this is actually the logarithm of the fluidity normalized by some value. But one of the nice parts we can see in this is, for example, there's this very, very hot spot here near this rift that was coming out of the Gibbs ice rise. And this is 2017 data. So since then, that rift has propagated all the way across the ice shelf and broken off a big iceberg. I think some of these red spots are areas of marine ice formation. Actually, we'll come back to this in a bit. But so there are really fun things that you can see out of those kinds of simulations. And I've also this is the newest tutorial that I'm trying to add as a demonstration of the heat transport solver. So the test case I want to use for this is Helheim Glacier in Greenland. So on the left is the surface velocity. So we then turned the crank in order to calculate the ice, the basal friction coefficient. And then I threw all that into the 3D model to try and figure out what's the ratio of how much of the ice flow is due to sliding versus shear deformation. So on the right, I've plotted the sliding ratio. So in the main trunk of the glacier where it's flowing fastest, pretty much all of the flow is due to sliding. But you get some pretty, you get some spots near these nunataks where much more of the flow is due to vertical shear. So Ian Jochen, who was my advisor, is now using this, and he's continuing some of the modeling work that he's done on Pine Island Glacier. So this is from a paper that he's working on now on simulating Pine Island under a variety of retreat scenarios. So I also have some students working with me. Before, the damage model that I showed you was stuff that Andrew Hoffman added. So Jess Badgley, who's also another grad student in earth sciences, wanted to use a shallow ice model, but I hadn't implemented it yet, and I thought this might make a good student project. So she did all this herself. And so we were trying to reproduce some results from a paper by Kessler from 2008, where they were using this kind of bed topography on the left to simulate sort of the mountain range, kind of roughly similar to what you might get on Baffin Island, and looking at how ice flows through these mountain passes. So this, I think, is a 12,500 year simulation, but we start with this kind of silly initial ice surface elevation, and it very rapidly relaxes and the ice starts to flow through those mountain passes. So we're looking at doing some more fun things with this like long-term climate coupling, and Jess is also interested in glacial isostatic adjustment, which is a very fun and interesting differential equation. So this is going to be yet another chance to do some fun finite element analysis. So roughly to wrap things up. So I think there are some new things that we bring to the table that kind of haven't been possible in years past. So we're trying to create some tool that'll help glaciologists do modeling who aren't necessarily experts in scientific computing. And at the same time, we also have to make it possible for the people who are experts to do new and exciting things. So the tools are there to run fast simulations, for example. And actually, I'll go back to the Icepack website here, which I briefly hinted at before. So we have some how-to guides, and one of them is on performance optimization. So here I was showing what kind of options you can pass to that solver object that I showed you before. Let's see if I can find it here. So making the right calls to PETSI to ask for really fast nonlinear solvers that will go quicker, but that might possibly explode. So if you want things to run fast, you're going to have to be willing to make some tweaks. But I also submit that the things that are going to make this, an easier experience for novices and that will help onboard people faster are also the same kinds of things that will help experts be more productive. So if you are already very acquainted with ice flow modeling, being able to spin up a simulation quickly and then worry about the performance issues later helps you kind of separate out the tasks better. And I think that the same thing is going to benefit both kind of people with a range of expertise. And also, I think we've done a pretty good job making it easy to experiment with the model physics and to kind of play around with things. So some new fun, shiny things that people are working on. So Andrew has done some work on this 2D damage mechanics model, but he's also working on kind of extending more into 3D, where we might be more explicitly accounting for crevasse depth and being a little more sophisticated about that. So Jess's main interest is in kind of interaction of ice and climate, and we're looking at adding a GIA model pretty soon. Ian, as I showed you, is doing this kind of continuing some of his existing work on modeling the evolution of Pine Island Glacier. And Ben Hills is another earth sciences student here who just started working with me recently. So we're developing a flow band model. So this was something that I don't really, I wouldn't use a flow band model myself. A lot of people have asked me about it, but I think it's something that's better used as a student project because I think it's something that's very reasonable to do and just to give people, give people the experience of writing code themselves and testing it and having fun with it. So I'm developing a model for the buoyant meltwater plume under ice shelves. It was the bane of my existence for a while, but I've started to enjoy it. So God help me, I'm doing some oceanography. So the end product of that, I think, will be that we'll be able to give you, calculate from some actual physical model what a sub-ice shelf melt rate is. I know a lot of people have used kind of ad hoc depth-dependent parameterizations for sub-ice shelf melt, which in the absence of running a whole actual ocean circulation model is basically the best you can do. So what I'm trying to write is something that'll give you a nice middle ground. So that's really a separate project. It's not part of Icepack, but I think it's going to be a really nice part of the whole if you're modeling tidewater glaciers. And finally, the next big thing on my agenda is a way to have a dynamic geometry and to have a calving front that moves. There's other kind of things we're working on and sort of on the data assimilation front as opposed to the modeling front. So Andrew and I are working on adding an ensemble comment filter. This is largely his effort. So Fabien Gilles-Cholet had a paper, I think, just this year or last on doing that. So we're going to try and do something similar to that. And part of my funding is from NASA for the ICESat-2 grant, which is we're going to do what I've tentatively called a reanalysis for ice sheets, where we're just looking at the past 25 years of observations with the hopes of kind of filling in and augmenting some of the gaps in the observational record as best we can with models, and also using this to do more ensemble prediction of what the ice sheets could be doing in the future. David Poloshenski is one of Martin Trufer's students at UIF, and they have a whole bunch of strain gauges on Athabasca Glacier in Alberta, which is sort of repeating an experiment that Charlie Raymond did at the same site many decades ago. So our plan there is to assimilate the strain gauge data into a flow model, which for me is a really interesting and exciting prospect because it's sort of an unusual kind of data source that, to my knowledge, most people haven't really used for that kind of application. And sort of in a similar vein, Jess is looking at assimilating ice core data and other paleoclimate proxies. So again, assimilating point data into this flow model, and especially something that has more of a integrated time history in it, is something that I think is going to be really fun and interesting. That's pretty much it. So I'll copy, let's see, I'll copy some of these links into the chat. But the first one I wanted to point out, and again, I showed that before, is the documentation. That's all at icepack.github.io. So we have some installation instructions, tutorials, and so forth, which we're constantly adding to those. So if there are things that you need to know that you can't find easily, you know. And second is the GitHub repository for the package. This is where all the development goes on. I've been a little slack in the last couple days. Sorry, folks. Busy preparing for this. And finally, the last thing I have on there is my email. So I've done most of the development so far. It's been great having students on this, and especially like the energy they bring to it is awesome. But at the end, I'm starting to reach the limits of what I can do largely on my own. So I'm trying to get more and more people involved in this because I think it has the potential to be really useful. Yeah, it's more fun with friends. And we have meetings every 10 a.m. Pacific time on Thursdays. So if you want to drop in, let me know. Tomorrow's Thanksgiving, so we won't be having it then. But that is pretty much it. I suppose I shall take questions. Oh, and Tavi wanted me to help advertise. Next week's talk is by Shin Sugiyama at Hokkaido University.
Thank you very much. There's some questions in the chat. I think the first one's from Heike. I don't know if you want to unmute yourself, Heike, and ask it directly.
Yes, sure. I was just wondering if you're familiar with the OpenFOAM computational fluid dynamics toolkit for C++, and in case you are, could you shortly describe its differences and similarities with Firedrake?
I have some passing familiarity with it. I wouldn't really know enough to comment. My understanding is their big application is things like aerodynamics, flow over cars, wings, that sort of thing. Have you used it?
Yeah. A few years ago, because my background is in aeronautical engineering,
right.
And the continuum mechanics, that's the same. So
yeah,
from the mathematical point of view, and I was just wondering.
My impression was that they were targeted more at like really performant implementations of solvers for more of a selected number of equations, and not quite as extensible to any crazy equation system you could dream up, which is just more a function of kind of what they were applying it to. But again, I haven't used it. You probably could answer that better than I could. Firedrake is like completely general. You could put in whatever crazy PDE you like.
Okay, thanks.
Cool. I see.
There's a question there from Julian. Do you want to unmute yourself? And Julian Williams.
Well, okay, I can read it. So Julian asks, do you think there's any real difference in using JavaScript as opposed to Python or any other language for analysis? Is it really just about preference? So there's a funny joke about this. You know, Churchill said about democracy, it's the worst system, it's just better than all the others. I really don't like programming language dogmatism. So I've implemented this in Python just because it sort of struck me as if a lot more people in the geophysical sciences are turning towards using Python as opposed to MATLAB. I know there are a lot of MATLAB users, but it just seems to be the way the wind is blowing. So JavaScript has the advantage of being able to run within a web browser, but I think the whole scientific computing ecosystem for it is, you know, and I know they have some stuff, but I don't know that it's quite at the level of sophistication of Python. In Python, you have tools like NumPy that are really fantastic. Yeah, I mean, I've written in a lot of languages. I used C++ for a while, and I did some commercial software development in C++, which is like, I was kind of at this point where I was like, oh, you know, maybe I want to go into the private sector. I'll try working at a tech startup. And I was like, nope, back to academia. So moral of the story, I hate C++.
Alexia,
Yes, thank you.
Hey, Alexia.
Hi, Daniel. Nice to see you.
Yeah,
Um,
likewise.
I was curious on how you measure fluidity on Larsen C,
Ah,
and how do you implement it in your code?
yeah, so I was a little vague about that. So by fluidity, if you write down Glenn's flow law, which is that the strain rate tensor is equal to some constant times the stress cubed, then the fluidity is that constant.
All right.
You can think of it sort of like the inverse of the viscosity. So fun and interesting fact, the fluidity is roughly an Arrhenius function of the temperature, and there's an activation energy in there. And the activation energy, I think, is exactly the energy of 2 hydrogen bonds if it's below -10 Celsius, which I think is just adorable. I think I learned that from Steve Warren. And the way that you, so the thing that I was trying to show off here is that, so the fluidity can't really directly be measured unless you were to go out there, fly onto the thing and stick a thermometer in the ice. But the point of the exercise is that since the fluidity affects the ice flow, then if you're also able to take some guess for what the fluidity throughout the ice shelf is and solve the equations of motion, then you can see how far off is the velocity that I get from observations. And using this information, you can go and try and back out what a sensible value of the fluidity was that would reproduce what you actually saw, which is an inverse problem.
Thank you.
Cool.
Thank
Yeah,
you.
and good to see you again.
Yeah.
Frank.
Yeah, good evening. Thanks, Daniel, for this nice presentation. Yeah, I have this philosophical question.
Yeah.
It's maybe not a nice question.
No.
It's the danger of open models. So what about the danger that people use Icepack as a black box? Because it's easily accessible, it's cool to use Jupyter notebooks, the tutorial is fantastically written, so it's very accessible. But then maybe, I mean, you struggled yourself to go through all the equations and so on, but then maybe others get the opportunity not to go through that damaging part.
Yeah. Well, the first thing I would say is that a shallow and superficial understanding is usually a prerequisite to a deep and profound understanding. The other, yeah, I mean, I see what you mean. I talked a lot about how I had to write all these finite element models myself, and I wrote my own loops and everything, and how much I hated it. But I learned a lot by doing it. So am I sort of depriving people of the pain that they should rightfully have? Maybe. Basically,
yeah, I understand.
but,
It's
but
a very
also, like, I mean, if people get interested in it, then I think it's an opportunity for them to feel empowered and like, oh, this is a thing that I can do. Like, this is reasonable. Whereas otherwise, they might just feel that it's inaccessible. And from there, I think it can provide a good jumping off point to actually, like, yeah, if you want the pain, you can have it. Is that?
Yeah, no, it's a very philosophical answer to that question. But I mean, a model is as good as its boundary conditions. And so it's also the boundary conditions that you put in there. Well, you explained that you can add more and more things, is also a limiting factor somehow, sometimes for modeling, because you stay with whatever the package provides.
I see what you mean. So okay, well, sort of to that point. So what the existing models provide is, so the diagnostic equations are expressed through a convex minimization principle, and there are several terms. So for example, the ice shelf flow model has a viscosity term, a gravity term, and then there's one for sidewall friction. So in principle, if you're sophisticated enough that you've used the existing models and are comfortable modifying them, then it's not completely out of reach to then implement your own model that has more terms in the variational principle. As far as boundary conditions go, so the examples that I've shown are not for like an entire ice sheet. So you have to come up with something that's happening upstream. But in principle, we could use this for whole ice flow, like modeling an entire ice sheet where that kind of is no longer a limitation. There are other things that are happening on the software side that make it easier to fiddle with those. I will say, when I, like 90% of the time when I screw anything up now, it's probably because of boundary conditions. That's another error-prone part that's kind of hard to really.
Yeah, and if I can stay on, so what about the computational speed if you compare it to, let's say, other codes that are either written in Fortran or in C++?
Yeah, no, that's a good question, because if I make something that's really nice and easy to use and it takes for bloody ever, then that's not really all that great. So I said that Firedrake will generate optimized C code for assembling the nonlinear systems of equations. The other side of the story is that it's built on top of PETSC, or the Portable Extensible Toolkit for Scientific Computation, which is this gigantic research code developed at Argonne National Laboratory. It's been around since '96. It has been battle tested 6 ways to Sunday, and it's better than anything I could ever dream of writing for things like nonlinear or linear solvers. And really what happens is the Python layer that you're actually interacting with is, in the grand scheme of things, quite thin. And when you ask it to solve an equation, really there's this huge apparatus happening below that all exists in C that is calling everything in PETSC. So I need to do more benchmarking. I believe that it is competitive. I honestly don't have the numbers to support that at present. It's something that's going to go in the paper about it, which is forthcoming. But I don't think that there are like large limitations that are stopping us from being competitive with codes that are written entirely in C or C++, because for the most part, the actual code that's running is all really optimized stuff that's in C. On top of that, so when you have a symbolic representation of the problem, there's high level knowledge that you have about the problem that can guide how you generate optimized C code. That basically the C code that it generates is faster than anything I would have written, and I've looked.
Oh, great. Well, I'm gonna try it out. Thanks a lot.
Yeah, let me know.
Really great talk. Yeah, thank you.
Yeah.
Question from Lynn.
Oh,
I read it.
yeah.
I was just wondering, you mentioned marine ice when you were talking about fluidity, and I was wondering if how difficult it would be to implement a depth variable fluidity.
So you can do it. It might be so there's a blunt and dumb way to do it, which is to just use the 3D model for an ice shelf, which is a little expensive, but basically I can do it. The more interesting question is, can we get the computational advantage of a 2D depth average model, but also have a depth variable fluidity? Yes, but I think it might be a little ugly. I think I can do it. So there would be some depth averaging part that occurs kind of in the middle there. Yeah, it's something I've thought about.
Gotcha. But the 3D model automatically, it doesn't have a depth average one. Okay.
Oh no, it's full like 3D.
Oh, awesome. Thanks.
You know what, actually, so yeah, no, let me amend that statement. You could use the 3D model for an ice shelf, and by a nice choice of basis, it'll barely be more expensive. So I will give you an unreserved yes, you can do it.
Cool, awesome.
Roger Clark.
Hello, Daniel. Thanks very much for that insight into the inside the black box. I mean, forgive a naive question from a passing seismologist who's meandered into the meeting, but it would be very interesting to be able to run this as what I call the equation engine inside a bigger process that would give you some. I mean, I'm quite keen on simple tornado plots, just showing the sensitivity of each different input variable to the final result, or even something more formal to an MCMC process.
Yeah.
I wonder how feasible it is to do that with your package. Thank you.
I have promised it to one of my funding agencies, so I better damn well do it.
Sorry to remind you.
No, it's cool. So the thing I'm looking at now is called Metropolis Adjusted Langevin, which is sort of a Monte Carlo like, or if you're familiar with Hamiltonian Monte Carlo, it's pretty similar. Mm-hmm. So this crazy Russian guy has Ivan Yashchuk, who I don't know how he's a genius or something. He makes me feel like an idiot. but so he wrote an interface between FireDrake and PyMC3. So there will soon be an interface to a Monte Carlo sampling package. So the answer to your question is yes, and I really want to do it because it sounds fun.
Okay, I'll watch the BBC News for the results. Cheers, thank you.
Thanks.
Okay, I think that's the end of the questions, and I think I am now sharing the advert slide for next week's seminar. So huge thank you to Daniel for this week's seminar. Lots of discussion there, that was brilliant. And just to encourage everyone to come back next week when I think we're going into the field again to look at freshwater calving glaciers in Patagonia. So please come along to Stephen Sugiyama's talk next week, and see you all there. And thank you very much again, Daniel, for this week's talk.
Thanks. And I put my email address in the chat and the website. Come check it out.
Fabulous. Thank you.